Okay, welcome back to the second class that we're going to have on machine learning. Today we're going to go over some statistics, a couple machine learning algorithms, and maybe some workflow automation if we get to it. I'll start off by just really quickly reviewing over some of the contents that we covered in the first lecture. So we started just introducing Python for machine learning, getting everybody set up in the Spider IDE. And then we went through some basic code using NumPy, Matplotlib, and pandas for importing, visualizing data, and processing that data as well. We're able to load in data from spreadsheet files and also the internet, we found out, using pandas primarily, although it was possible with NumPy, just stick to one algorithm and just use pandas. Starting to understand our data. So by looking at it using Matplotlib to visualize the data and various things. And then also some of the pre-processing that we need for machine learning. So this is kind of like the biggest step and most important step that you need to do. It's fairly easy to set up a machine learning algorithm, as we'll find out in today's lecture. And the most important thing is understanding your data and figuring out what your data types are, how to format your data and condition it so that it's ready for whatever machine learning algorithm that you choose to use. So today we're going to go over some simple feature selection for machine learning, and then subsampling mechanisms. So in particular, KFold cross-validation is what we're going to look at, and then the statistics that we can use to describe the machine learning algorithm. So when you use a bunch of different algorithms, you're going to have various metrics that you can use to evaluate how well they work. So the most popular one is accuracy. It's conceptually easy to understand. You can compare the accuracy of different ones, but there's also more than one way to compare machine learning algorithms, and we'll go into other ones there. And we'll go through a few different types of machine learning algorithms. So there's two general problems. There's classification and regression problems. So classification is when you have a label. So for example, in our Pima Indians data set, the classification is whether or not somebody has diabetes. And then there's a Boston housing market data set as well, where the linear regression variable that we're trying to calibrate to is a price of housing. So that's not like a 1 or a 0 label. That's a continuous variable that goes from some number to some maximum price. So we will start with chapter 8 over here, which is feature selection for machine learning. So for feature selection, basically what it is, you look through your data through some sort of algorithm and try and reduce the dimensionality of your data. This is important because if you can describe your problem with less data, then you're less prone to overfitting. It can help improve the accuracy and really can significantly reduce the amount of training time that you need. So there's a couple different algorithms that are presented in this book. The first is univariate selection. There's a recursive feature elimination and principal component analysis, which I think that you guys have probably touched on and tried to do some hard math. We'll go over PCA in particular. I'll kind of skim over the univariate and recursive feature elimination. We'll go into that just first. So if we run this code here, so this is univariate selection.py. Essentially what it looks like it does is you select the k best features to extract. So here, out of the 8 features that we have in the data set, so just to remind you, our data frame is here. So we have on the index axis over here all of the different patients. There's 700 of them. And then we have 8 different descriptors here. And then our class variable at the end, which is our answer. That's our Y matrix. So a 1 represents if they have diabetes and a 0 if they don't. And what this algorithm seeks to do is we specify 4, and it looks for the 4 best features here to help predict this class. Univariate feature selection is almost never good. It's a recipe for underfitting. I don't recommend it. So I'm just going to leave it there. You can do recursive feature elimination as well, which is kind of like the univariate one, except it tries to converge to its 3 best values here by itself. But I won't really go into this one either. We'll just go into PCA because it's much better to use a multivariate model since PCA considers all the dimensions. So I will bring up the PCA code over here, and it's actually quite simple. But before I explain this code, I'll just really briefly go over how PCA actually works. So essentially, PCA is what's called an unsupervised learning algorithm. So what it seeks to do is look for covariance within the data set. So the steps to how it actually works is first you take all of your data and standardize it. So you subtract it by the mean and divide it by standard deviation. So then you get a mean centered at 0 and a standard deviation of 1. And what that does is it ensures that all of the different data that you have is on a comparable scale for the next measurement, which is computing a covariance matrix. So essentially you compute the covariance between each of your data points. So on the diagonal over here, this is essentially just the variance of your data. And then on the off diagonal points, you get covariance between them. So essentially the number of variables that you have for your data is the dimensionality that you're going to have for this covariance matrix. So for instance, in our data frame over here, we have 8 different variables for each sample. So what we would end up with is an 8 by 8 covariance matrix. Then we get to go into some fun linear algebra. So what we do is we compute the eigenvectors and eigenvalues of this matrix, of the covariance matrix. And you end up, this is a great spot to show it, maybe a little further down. Right. So for, say your data has 2 dimensions and it's scattered like this, essentially what PCA does is it seeks to find the axis with the highest amount of variance explained, and then each subsequent principal component is in an orthogonal dimension. So what this shows here is a rotating axis where it's trying to find the principal component, the first principal component, which would minimize the distance between each of these points and the line. So trying to minimize the residual is what that's called. And once you find that, principal component 2 is oriented orthogonally to that. So if we wait just a few more seconds here, the principal component 1 axis will be aligned when it's right here, where each of these red lines here, the residuals are minimized. And then principal component 2 is just by definition orthogonal to that. And this can be extended up into many, many, many dimensions, and it becomes pretty much impossible to think about if you go beyond 3 dimensions. So what you end up with is, say you have two variables for each of those, like we had in that example there, you end up with 2 eigenvectors over here and eigenvalues associated with that. So the eigenvalues are, they describe which components are contributing most to the overall variance. So if we have lambda 1, which is the highest eigenvalue, we're going to designate that as principal component 1. and the second eigenvalue is principal component 2 because it's less than that. And for our example, we would get 8 of these eigenvalues and we would sort them from highest to lowest, and that would define our principal component 1, principal component 2, all the way down to the nth principal component. If you want to determine what percent each component actually contributes to the overall variance, what you do is you sum all of the eigenvalues, and then you divide each of those eigenvalues by that total. So if you do that, you would have 1.28 plus 0.04, so you'd have 1.32 as the sum of all the eigenvalues here. And then if you divide 1.28 by 1.32, you get 96%. And if you divide 0.049 by 1.32, then you would get 4%. So in higher dimensions, like this example here, you would have something like your first will be explained by like 40% of the variance is in the first principal component. Second is in the or 20% in the second principal component, about 12% in the third principal component. And the goal here with PCA is to try and do dimensionality reduction. So if you can describe like 80 to 90% of your data within the first 3 components, it's likely that's all you need to actually describe. So you can use all of this fancy linear algebra to help you reduce the size of your dimensionality by doing this math here. So you can back calculate to your original features using this. And it's really common that people do PCA as a first step for machine learning. If you open up the MATLAB toolbox, what you'll find is the very first button for machine learning is a pre-processing button that says PCA. So it's really, really standard that people do this. And you can, at a later point, go through line by line of how the PCA actually works, but that's kind of the general gist of it, is to just redefine your basis set so that it's aligned along an axis with the largest variance, so you can reduce the dimensionality of your data set. So I will run this code. I think I already ran this. So then you have explained variance. So if we want to take the best 3 of them, we get the first principal component in our data set is explained by 88%. The second one is 6%, and the third one is 2%. So we can effectively reduce our dimensionality of the data from 8 to 3 while maintaining like 99% of the overall variance in the data. So that's pretty much it for feature extraction. I think in Roman's class, you actually did a lot of the math behind this. And that's commendable for sure. So what you can do instead of the math in Python is you go pca.fit of x, and then you get your fit. And that's great because no one wants to do the math by hand, and I would definitely do it wrong if I tried to. So I'll leave it at that for PCA, and just know that it's a really nice pre-processing step that you can do. So with that, does anybody have any questions? Okay, so we will move on to chapter 9 here. So now we get to do the fun part, which is evaluating the performance of machine learning algorithms with resampling. So I'm just going to read this here. You need to know how well algorithms perform on unseen data. The best way to evaluate the performance of an algorithm would be to make predictions for new data to which you already know the answer. That's not always available to you. So the second best way is to use clever techniques from statistics called resampling, which allow you to make accurate estimates for how well your algorithm works and will perform on new data. So essentially, this is just a strategy for you to take a subset of your data, reserve it on the side, use the first data set for training your algorithm, and then your reserve data set for evaluating how well it performs. So there's a couple ways that people do this. They do train and test sets. So you can just by hand pick out ones that you want to use for your training set and which ones you want to use for your validation set. And if it sounds like cheating, it kind of is, I don't recommend using that. What people mostly use is KFold cross-validation or some repeated random test train splits. So what I'm going to do here is first just explain KFold cross-validation. So we can find that down here in my thesis chapter. I have one figure that shows us how to do that. Aha. So KFold cross-validation is a way to partition your data set. So for instance, let's say I have this number of samples, some n number of samples, and I want to do KFold cross-validation. What KFold does is it will split it into k number of even subsets to evaluate, and it will iterate this algorithm k times. So let's say, for instance, I have 5 samples and I'm looking to do 5-fold cross-validation. What it will do is, in the first instance, it will reserve the first sample for validation and then use the remaining 4 samples for training. So it'll train on these samples and then evaluate it on the first one. The second time the algorithm goes, it will do it on the second one over here, and third one, and so on. So you can do this for, say you have 1,000 patients in your database. A typical value for a KFold cross-validation is 10. So what that means is if you have 10 even folds of 1,000 patients, you will have groups of 100 validation patients for each time the algorithm executes. This is kind of the gold standard of subsampling, and it allows you to have an idea of how well your algorithm will work on, in this case, 10 different subsets of independently validated patients. There's also something called leave one out cross-validation, which is more statistically rigorous, but takes a very long time to actually perform. So in that case, you set k is equal to 1, and essentially you take one patient and then you save one patient for validation, and you train the network with the remaining 999 patients. And then when you're done with that, you go on to the second patient and you train it with the other 999. Then you go to the third patient. You could imagine you have to iterate this for as many patients as you do have. This is the most rigorous way to do it, but it's very computationally intensive. So it depends on the kind of resources that you have. Typically, people will do a KFold cross-validation of 10, which is a 90%, 10% split on your training versus validation data. A lot of the times with our Raman algorithms, we do something like a 70-30. It really depends on your application, but 10 as a value is a really good place to start. So I'll come over here and we'll start looking at that, chapter 9 here. Okay, so here's the train test split. So you just define a fraction that you want to split, and there's a train test split function that comes from scikit-learn. And what it will do is it will take in your X and Y matrices over here, your test fraction, and some random state, which is identified by seed. So I think there's 7 of them that it's going to make. And then it will spit out an X training, X testing, then Y training and Y testing as well. So it'll handle all the partition for you for both the X and the Y variables. And then what is it using here? Doing some logistic regression on this. And our accuracy is 75%, which is what it is. We're going to go from here to I guess we can just do shuffle split. So this one's a little bit better. It's a lot like what we just did, except in this case, it's going to randomly permute the order of all the patients every time it does a split. So it's a little bit less biased, which is kind of nice. So we can run this one. And we see that the actual value doesn't really change that much. We can run it a couple times. Oh, that's interesting. I figured that it would actually randomly shuffle it the way that it says shuffle split. That's a little bit misleading there, because these values here should be dependent on the initial seeding. But it turns out that it's not. That's probably to do with this random state variable, which I don't actually know too much about. But that's not really so much of a problem, because I don't recommend that you use this anyways. You should be using cross-validation. Okay, so let's see. So this is our KFold cross-validation. So we just load the values in the same way that we've always done it. And then you define this KFold variable. So here you define the number of splits that you want. And then there's this random state variable here. I think random state is actually, I think there's some like hash table that's built into the back of this, which is just pre-calculated, that has a bunch of like randomly selected numbers that it can look upon to simulate a random number generator without actually having to use one. But anyways, we have the KFold split over here, and we're going to use a logistic regression. And what we do is we evaluate that by using this cross-val score from scikit-learn. So that takes in our model, x, y, and then for the cross-validation variable, it takes in this KFold, which we've defined up here. So if we do that, what we end up with is accuracy of 77%. And across 10 of those scores, so we have results here, we have the accuracy from each of those folds. So this is the first fold, second fold, third fold, fourth fold, all the way up to the 10th fold. And all this does is it takes the average of all of these and will spit out an overall accuracy of the model. This is really important to understand, because with something like 1,000 samples or 760 samples, it's a lot when you're doing experimental work and you're gathering hundreds of samples. But in the context of machine learning, you'll see that people are using like millions and millions of samples. So you're hoping that when you have like millions of samples, you're not really going to have a lot of selection bias, but it still tends to happen. And what you can see is, depending on the subset of patients that you're holding out for validation, sometimes the model works a little bit better, like in this case with 83 and 85%. But in other cases, it works like 68% of the time. So it's really important that you use something like cross-validation, which gives you an unbiased way of subsampling your data set. We can move on to, before we move on to leave one out cross-validation, does anybody have any questions about how KFold cross-validation works?
I have a quick question. For the random state, you say equals 7, but why is that particularly 7?
Yeah, it's a good question. I'm not exactly sure why it's 7. So I'm just going to look that up here, because I'm not sure. Random state Python split. Yeah, so that it's as I thought. It's used for initializing the internal random number generator. So we could choose a different number here. It's using the 7th one for some reason. Maybe I can change this to 5 and it will do a different one.
Okay, so you just choose the value that give you the best value then on the results.
Yeah, in theory, you should, it really shouldn't matter which one you choose. But you can see here, this one here was calculated with it as number 7. This one here was calculated with it as number 5. And then I tried with number 5 again, and it gave exactly the same answer. So it's splitting the data in exactly the same way every time. And it's not actually using a real random number generator to perform which one it's going to split.
Okay.
Yeah. So in theory, you really shouldn't have to worry about that, but you can play around with it if that's of interest to you.
Look, if you want, you can go to page 58 of the textbook, and they have a little paragraph on random seed. They elaborate a little bit more.
You said number 58?
Yeah, 58. It's one paragraph in the middle, below the table, below the code.
So please the random seed.
Yeah, they say by specifying the random seed, we assure that we get the same random numbers each time we run the code, and in turn, the same split of the data. This is important if you want to compare the result to the estimated accuracy of other machine learning algorithms. Okay, that makes sense. So if we're looking at, say, we're doing KFold cross-validation just to get a rigorous performance metric for unseen data, but we'll also want to compare that to a bunch of different machine learning algorithms, then we want to make sure that we have the same subset of patients for every time KFold cross-validation runs for each of those machine learning algorithms. So I think that's a good choice to use, and we'll get to that a little later when we start comparing these algorithms together.
Okay, yes, perfect. Thank you.
Yeah.
So what if the accuracies were extremely different for the different random states? Because it just kind of seems like you could cheat. Like maybe, I don't know.
Definitely. So one way that you could not cheat is by using leave one out cross-validation.
Okay.
Yeah. So yeah, this is a perfect way to lead into this. So basically what you're doing is for one patient, you're using the rest of the patients to calculate that. And I think in this data set here, it probably won't take too long. I use leave one out cross-validation for my ECG data, and it takes me about a week to generate statistics for it. Here, we'll probably be able to generate it basically immediately, but you see that I don't have an answer right away. And let's see the results here. Yeah, so what we end up with is a result for each of the patients. So in the previous data set, we had in our results, we had an array of 10 accuracies. So this was 83% accuracy in the first fold, 71% accuracy in the second fold. Now we have these here, which is 100% accuracy in the first fold, 100% in the second fold. And this is just telling you whether or not the algorithm got the patient correct or not. So let's see, accuracy here is, yeah, so it goes through results. It gets the mean and multiplies by 100, and then also the standard deviation. So this is interesting. So the standard deviation is huge. That is actually massive. It is the most rigorous way to explore your data, but depending on your data set, it may or may not really be feasible to do, especially not only depending on the size of your data set, but the machine learning algorithm that you choose. So if you do something like a convolutional neural network, it takes a really, really long time to optimize the features that you're using, that you're feeding into the actual neural network part of it. So if I were to use a convolutional neural network on my ECG data to do leave one out cross-validation, it would take over a year. So we decided not to. That would be a very long time.
So I guess if you have super different like accuracies from the different random number generators, but you didn't have the means to do leave one out, would you just say, like, explain your situation? I don't know.
This is
Like-
typically what's presented in journals. They will do K-fold cross-validation and will report some sort of accuracy and a standard deviation.
And
So,
just one number. Okay.
yeah, and they'll
Okay.
report it just like this. This is the norm in a lot of journals. What you'll see in some medical journals is the first figure is typically a patient flow chart where they show how they started with all their patients and whittled it down to their actual usable data set. Sometimes they get rid of people due to technicalities, privacy issues, people moving during an ECG, for instance, and that kind of thing. And the norm in those journals, which has been around for a really long time, is that you just grab a whole section of patients and reserve them on the side, no matter what, as independent validation. And this is kind of a way for the doctors to look at the statisticians and make sure that you're not cheating.
Okay, that makes a lot of sense. Okay, thank you.
Yeah, no problem. So yeah, you would just train it on all of your data like this, and then you would basically take all of the training data and create like one neural network, for instance, and then apply that neural network to everything in your validation data set and report that accuracy. Okay. So if we're all comfortable with this subsampling techniques, then I think the next chapter is moving on to statistics. Okay, so Kevin sent something over here. It says, in this manner, if you change your model by either changing hyperparameters or machine learning algorithms and retrain it, you can be assured that any differences happen due to changes to the model and not due to having a different random validation set. So yeah, this is talking about that seed number. That's exactly right. Just to make sure that you have the same data set and that you're comparing apples to apples with the specific patients that you're actually using. Okay. Okay, so for performance metrics, the obvious one is what is the accuracy, and that's what we've been looking at this whole time. And it depends on the data set that you're looking at. So as I mentioned, we have the Pima Indians data set, which is the onset of diabetes. And this is a binary classification problem where either you have a 0 or a 1 as the answer. And for regression metrics, you have a data set, for example, like the Boston housing price, where you have a bunch of input variables and your output is the price of the house. And that's a continuous variable. So you can't really calculate an accuracy per se for that. But what you could report is something like our root mean square error or an R-squared value. And we'll get into those things. So for classification, what we're going to look at is classification accuracy, logistic loss. We may not dive into that. Area under the curve, ROC curves, confusion matrices, and then there's a classification report that they go into. So we will go over here and start with chapter 10 in the classifications. So the first thing that I want to go into is a confusion matrix. And a lot of people have been confused by these, and it's part of the name, and that's kind of what makes sense. Essentially, a confusion matrix is this matrix that we get right here. And that probably doesn't really give you a whole lot of information about it. So what I'll do is I will come over here and refer to my thesis for a nice figure that I think illustrates things really nicely. So confusion matrix is a contingency table which plots the true conditions versus the predicted conditions. So we know the answers to our supervised learning algorithm for classification. Either they're truly a negative and truly a positive, and then we make predictions on it as well. So either we will predict them as negative and predict them as positive. So in the case where we know that they're a negative and we also predict them as a negative, that's a true negative. If we know they're a positive and we predict them as a positive, then we have a true positive. If we know them as a positive, but our algorithm predicts them as a negative, that's a false negative. And if we know them to be truly negative, but our algorithm predicts it as a positive, then that is a false positive. So this table, we basically populate with the statistics for the number of true negatives, the number of true positives, and the number of false negative and positives as well. What you want for a really good classifier is to have a lot of numbers on this diagonal here. That means the predictions that you've made are actually true, and as few as possible on the off diagonals. So these are your false negatives and false positives. So the accuracy is the total number of true negatives and true positives. So it's this space plus this space over the total number of patients that you have. So you sum absolutely everything together. And then there's these values called specificity and sensitivity. And this is what the doctors are really interested in. So these basically tell you, out of the patients that are actually negative, what is your accuracy? Sensitivity is, out of the patients that are actually positive, what is your accuracy? And then the computer scientists are interested in this one over here. So it's, out of the ones that you predicted to be negative, how many of those are correct? And out of the ones that you predicted to be positive, how much are you actually correct? Doctors actually really like this negative predictive value, because this one is an assurance that if you give a patient a negative diagnosis, then you can be confident that they're actually negative. So they really like this one, but most people will just look at accuracy. And that's definitely a good place to start. And to make things even more confusing, there's even more of these metrics available. These are the basic ones, but I'll forward over to the Wikipedia page here, where you have that same table that we had here. So we have true positives, true negatives, and false positives. And then you get all these things like the sensitivity and specificity. And you get these balanced accuracy scores, Folks-Mallow's index, and there's so many of these things that you can calculate. Diagnostic odds ratio is something that's pretty popular. And on the side over here, what you'll see is how to actually calculate each of those. So depending on the metric that you want to present, all of it's available here on this Wikipedia page. But generally, you're probably just going to look at accuracy for the most part. And then if you're specifically interested in what your accuracy is for positive patients or negative patients, then you can use something like sensitivity or specificity. The way that I actually calculate that in my code here is I calculate my true positives, true negatives, false positives, and false negatives, and then the total number of positives and negatives, and then I just calculate all of them directly here. I don't use all of them, but they're all available to me if I need it. And you can calculate them exactly like this if you want. You probably won't need to go this far into depth with it, but the real ones that you want to know are accuracy and then this ROC value. So area under the curve receiver operating characteristic is what it's called. So before we move on to that, we'll come back to this confusion matrix over here. So now that we're a little less confused about it, what we see here is that on the diagonals, we have 141 true negatives and 51 true positives, and 21 false negatives and 41 false positives. I think that's the way it works. These ones on the diagonal are definitely the correct ones, and the ones on the off diagonal are definitely incorrect. And then if we wanted to calculate the accuracy, we would have 100 times 51 plus 141 divided by 141 plus 21 plus 41 plus 51. So now our algorithm has a total accuracy of 75.59%. Is everybody okay with the confusion matrix? Okay. So now we're going to move on to the area under the curve receiver operating characteristic. It's a huge mouthful, but we'll go through it, I promise. So what this really depends on is a true positive rate versus a false positive rate. And these are the numbers right under here, sensitivity and specificity. So this is our true positive rate over here, because the true positive and then the rate of true positive comes down here. And then specificity is the true negative rate. So they are truly negative, and then it's the rate that we're able to predict them as being negative. So coming back over here, I'm going to start here. Let's say that we have, how many samples are here? Let's say 30 samples. And the ones here that are labeled red are actually negative patients. And the ones that are labeled green are actually positive patients. If we have a logistic regression model, it's going to output some number between 0 and 1, which is the probability of a positive diagnosis. So if you have a value close to 0, you have a low probability of a positive diagnosis. And if you have a value from the model close to 1, then you have a high probability of positive diagnosis. So since the values are scaled between 0 and 1 and not exactly all 0 and exactly all 1, what we have to do is define something called a decision threshold. And the decision threshold is you got to draw a line at a specific value where you say if your predicted probability from the logistic regression model is lower than this value, then you're going to be assigned a negative prediction. And if it's above that value, then you're going to get a positive prediction. So if you look at this data, the particularly difficult area is right here. There's no clean line that I can draw, which puts all the red points on the left and all the green points on the right. If we were to have that, then we would have a perfect classifier. But in this case, we don't. So there's a trade-off essentially between the true positive rate and the true negative rate. So let's start from the left. So if I say my decision threshold is 0, which means that everything is assigned a positive diagnosis. What that means is we're going to have a really high true positive rate and a really low true negative rate. Here we're doing true positive rate versus false positive rate. So what we'll have is a value way up here in the top right corner where we have a lot of false positives and we have a lot of true positives as well. And that's no good. That's not where you want to be. So the way that this ROC curve is generated is for each patient, you test and see what your true positive and your false positive rate is. So as we move along here, what we see is that our true positive rate stays the same, but our false positive rate will decrease. And as you go along further and further and further here, you end up creating this ROC curve. So for each patient, you get one data point where if you use that patient's regression value as your decision threshold, you'll have a defined true positive and false positive rate. This is the preferred metric for evaluating how well your machine learning algorithm works. So you end up with this curve here, and it's called an AUC ROC curve. So area under the curve, that's this shaded area over here, and that's what you're trying to calculate. So there's a couple interesting things about this. The first is that if you have a truly perfect classifier, what you end up with is a curve that appears in this top left corner. So you want to maximize your AUC value. If it's exactly 1, then that's a perfect classifier. That means this whole entire area is shaded in here. If you have a classifier that has no skill, so essentially for each patient, you're just flipping a coin, 50-50 going either way, what you'll end up with is a diagonal line across here. That ROC value is 0.5. And if your classifier has some level of skill, then the curve is going to be somewhere between that diagonal line and something that just merges into the top left corner over here. If you have something that curves underneath a no skill line, then it's making the wrong prediction more often than not. And what people will do is they'll just flip the answer that it gives. I recommend trying to solve the problem a little earlier than that because it's a bit of a band-aid solution, but I do see that happen sometimes. I think there's a good check your understanding here. So this is exactly what I'm talking about. A curve like this basically means that you're giving a wrong answer more often than not. This curve over here means that you have a perfectly inaccurate classifier. So you're getting it right 0% of the time. So you should just flip your diagnoses. And these 3 here is realistically what you're going to see in the real world. So this diagonal line, that's your no skill, flip a coin. This one right here is your perfect classifier. So you just get a box looking thing here. And the area under this curve is equal to 1. And then realistically, most classifiers you see will have some sort of curve like this. And you can calculate that for each kind of classifier that you have. So I will run this classification AUC code. Does this give you any plots or anything? It does not. So you get a value of 0.826 for the ROC using the logistic regression, which is actually quite good. That's better than 0.5 considerably. And then 0.5 here is the standard deviation across 10-fold cross-validation. So the results here, these are the ROC values for each of the folds that are calculated. So you'll see that some of them are a bit better, up to 0.92. Some of them are a little bit worse, going down to 0.81. I did write something a little bit more comprehensive than this. So I will run this. So you can find this code afterwards in the Luke Python scripts directory in the Google Drive. So I think this one here, I actually had it plot an ROC curve. But it was kind of weird to teach it without the actual curve itself. So let's see, is there a plot here? There it is. Okay. So essentially what I did is I didn't do any kind of KFold cross-validation or anything. I just took all the data, X and Y, and I fit a model to it, and I've got results here. So define logistic regression model.fit on X and Y, and then I go ahead and use the model and predict all of my Y values. So these are your Y hat values here, which I labeled as results. So when you're reporting these ROC values, typically you don't get some sort of plus minus value. You just get one value because you're adjusting your decision threshold across all the patients that you have, and you end up with one value. But if you're going to take that and submit that as a result with your accuracy and everything, there's going to be some reviewer number 3 that knows a lot of statistics, and he's going to say it's not good enough. So what we use is the DeLong statistics to calculate a plus minus value on this. And there was a hero of mine that I found on Reddit that created this database here for actually computing all of the DeLong statistics. So not only will this give you error bars on your AEC value, so that's what's described right over here, that plus or minus 0.033. It also provides you a way of comparing different machine learning algorithms by their ROC values. So we're going to, in the next lesson or so, like next couple lessons, we're going to look at how a bunch of different machine learning algorithms actually work on the same data set. People will typically compare the accuracies together, but the preferred way of comparing how well machine learning algorithms work is by comparing the ROC values. And this DeLong function toolbox will give you methodology for assigning statistical significance to how the results between different algorithms performance actually works. So over here in this logistic regression example, we end up with an ROC curve that looks like this. The value is 0.72, and that's what it is. You can see over here on the diagonal, this is the no skill. So that's as if you're flipping a coin. And then this is the actual ROC curve itself. And then this green point here called threshold, that's the decision threshold. And for this, I've assigned a decision threshold of 0.5. So you just essentially round the output, and that's typically where you would start. So before we move on to the Boston data, does anybody have any question about these ROC curves? Okay, we'll move on to the Boston housing data. Oh, hold on, I think we have one more left here, classification report. Let's see. Okay, so this one here, this classification report is a function that will generate some of the data, some of the performance metrics that I showed you in this big complicated Wikipedia page over here. So all these values over here, which you can calculate using these formulas on the right, sensitivity, specificity. Some of the more confusing parts is something like positive predictive value is also called precision. Sensitivity can be called recall or hit rate or true positive rate. So there's a lot of nomenclature that means exactly the same thing. So you got to be careful about what they're actually calling it, but you'll see some values here like precision and recall, and it'll do some of these things for you automatically if you call this function. But what I actually do prefer to do is this way, where I can assign real labels to the data, and it gives you a little bit more control over everything that you're doing. And I'll go ahead and take this code and put it in our repository on the Google Drive as well for you guys to look at. Okay. So now we will go into regression. I'm just gonna close some of these terminals here that we don't need anymore. Okay. So now we finally have a data set that's not for classification. We have one that's used for regression. So our Y value here is the 13th column, which is at the end here, median value. I assume that's what it is. And this is the median value of a house, probably not in dollars, maybe in hundreds of thousands of dollars, millions of dollars. I don't know how much housing is in Boston, probably more than this, and US dollars, I assume as well. And then these are our input variables over here. So essentially you do a plug and chug the same way that it's always been. You have an X matrix of values and you're using machine learning to try and create a function that maps these input values to this output over here. So there's a couple different scoring metrics that you can use. This one over here uses the R² value as a performance metric. So you're just trying to draw a straight line in whatever hyperplane is this. So we have 13 variables here in total. So you have a hyperplane in 12 dimensions that you're trying to draw a line through, and you use the R² value to evaluate how well that's working. So in this case, we have an average R² value of 0.718 with a standard deviation of roughly 0.1 over 10-fold cross-validation. You can use the mean squared error as well. So that's an absolute amount of error there and standard deviation associated with that. And then there's a mean average error as well. So there's no example here, I think, for root mean squared error. I think that's what's usually used because it's normalized, a little bit easier to understand because we look at -23 and -3.38. If we don't have a really good hold on exactly what the numbers are in the data set, then it's hard to know. But like, for instance, with this R² value, we know that the closer to 1 that value is, the better it works. So if you don't really know the data set that well, then R² is probably good. I believe the RMSE value is actually preferred. And I wonder if that's actually possible here. So let me see. RMSE scoring, sklearn. I'm going to try something bold here and just guess what that syntax might be. And if this doesn't work, then I'm going to leave it alone. Root mean squared error. It is not a valid value. So I'm not exactly sure how to do it. I don't really have any experience myself with doing regression classification or regression problems. I've done all classification problems myself. So if you need to predict something on a continuous variable, there's actually a textbook by this author that is for doing regression problems with machine learning. In these cases here, I'm mostly going to stick to classification, but a lot of the principles that you use are going to be able to go back and forth between both regression and classification problems. Does anybody have any questions about this? Okay. And yeah, the if you go into this over here, so under this directory, the Python scripts, go into the code, you'll have something that looks kind of like this. In chapter 10, you can just copy this DeLong functions into your directory. And this is where I did all of this. So it has all of this DeLong functions from that guy on Reddit and the example of how to use it as well. So we will move to chapter 11. And now we'll move into some different classification algorithms. Okay, so we will be looking at Gaussian naive Bayes, logistic regression, linear discriminant analysis, support vector machines, classification and regression trees, k nearest neighbors, and it's going to sound redundant, and coding it is actually quite redundant. So as I flick through all of these files, you'll see that just 2 lines are actually changing here. So the first line is this one here, where you're importing the specific machine learning algorithm from the scikit-learn database. And then this line 13 here, where you're actually defining that as your model. So we can go through each of these and see how it works. It'll give you an accuracy and it's a little redundant. What I will go through though is how support vector machines work. So these are really popular. I'd say probably the second most popular algorithm besides neural networks, which is something we'll get into a little bit later, maybe in a few lessons, or maybe the next one even. So support vector machines are essentially it's a function that will map your input data to your output data. The nice thing about SVMs is that you can use it both for classification and also regression. So it's quite popular there. The goal of any kind of classification problem is to draw some sort of boundary or decision threshold where, say in this case, where you have red squares and blue circles, if I draw a line somewhere here, I'll be able to say, okay, everything to the left side of this line is going to be the red squares, and everything to the right side is going to be these blue circles. But I don't know where to draw that line. That's something that's difficult for me to do with my eyeballs perfectly. And the good thing about support vector machines is that it will figure out where that line should be. So, you have this kind of line here, vertical line, and it will figure out the best place for it. So the support vector machine is a machine, which is the algorithm that identifies these support vectors. And the support vector is the minimum distance between the closest data point from each class to your optimal hyperplane that goes in between your data points. That's where all the words in the name come from. Support vectors, and then the machine is going to optimize this line over here to minimize the residual value between the closest ones here. If all classification problems were this easy, we probably wouldn't need any complex algorithms, but they're definitely much harder. So even if you get to something like this, where you have the circles and squares again, your eyeballs can draw a circle around here, but you can't draw a linear line that goes through there. Luckily, what a support vector machine can do is automatically define a new basis set where these variables may be linearly separable. So for example, if we define a variable z is equal to x squared plus y squared, what we end up with is being able to transform this data over here to this data. And then it becomes easy to actually draw a hyperplane through that. And then you can back calculate it and project it onto the original basis set, x squared plus y squared. And then if you identify z is equal to k here as your decision threshold or your hyperplane, then that becomes this purple circle over here. For support vector machines, there's a couple parameters that you need to tune. One is this C parameter. And you can think about this as if you're trying to say fit a polynomial to some data, if you use too high of a polynomial, what you'll end up doing is creating a line like this, which overfits your data. But if you select something that's too low, then it's going to underfit your data. So C is a value that you need. It's a hyperparameter. That's what they call. It's a hyperparameter that you need to optimize for your data specifically. So it's not necessarily just a straight line that goes through the data. And that's because SVMs are nonlinear functions. The second one is this gamma parameter. So basically gamma is a parameter that you tune, which will determine how much influence data points that are far away from your hyperplane actually influence where that hyperplane is. So typically what you'll do is you can start with all of them will influence it exactly the same, but if your points are really far away from the hyperplane, the precise position where the hyperplane exists probably isn't going to have much of an influence on how accurate the prediction is on these far off points. So what you want to do is you want to weight the points that are closer to the hyperplane to have more influence over where that's actually placed. And this makes sense because you're trying to find this support vector, which is the minimum distance between that hyperplane and the closest value in each of those classes. So that's kind of in a nutshell how SVMs work without doing any math at all. And I'm going to leave it at that amount of math. And you know what I'm going to do? I can go through and just run all of these in different windows. I'm not going to go through and tell you how all of these algorithms work in depth. So I believe the next chapter is how to compare all of them directly in one piece of code. So let's go to that. Okay. I will do that first and then come back to chapter 12, which is the regression. Okay. So here we go. This is much better. So essentially, this is exactly like the codes that I was running before, except what we do is we import all of these machine learning models. Oh, here we go. Machine learning models at the top instead of just one of them. And then we have our X and Y data as we always have. And what we do is we generate a list of models. So we have the logistic regression, linear discrimination analysis, k-nearest neighbors, decision trees, Gaussian MB, and I actually don't see the support vector. Oh, is this? Oh, SVC. It's weird that it's SVC and not SVM, but there it is. So if I were to run this, isn't that nice? We get an accuracy and a standard deviation across the KFold 10-split cross-validation for each of the algorithms. And I believe that there's actually a plot here. Yeah, this one here. I'm gonna move everybody up. That shows a comparison between the algorithms. So on the left-hand side here, we have accuracy, and I'm gonna go ahead and
sorry, just one real quick question. Why is the line of the KFold inside the loop? Is there any need? I will have just put it outside.
yeah, you could probably put it on the outside.
Because then that way just makes, I mean, we're giving it the random state, so the KFold is going to be the exact same one, no matter how many times you do it. But just having it outside the loop gives me the certainty that it's going to be for sure the same like folds for every single one of the models. But yeah, I guess it doesn't really matter as long as it's specified the random state. It can be in or outside the loop.
Yeah, we can try it. So I can just take this and place it out here. Let's see if this still works. Yep, it's exactly the same. So this is a nice way where you can actually for sure ensure that it's going to be the same and not really have to worry about the random state. This is a good way to ensure that you're for sure using the same one. And I think just for making it clean, they just take the same code that was in the previous ones and we'll loop through all of that for consistency. So I'm going to go ahead and you can definitely do it this way and that's fine, but I'm going to leave it the way that it was in the original code like this.
There's a very subtle difference for the cards for the 72, but when the code was in the 4, it was a little bit different.
I have Yeah, it's a little bit different. So essentially, what you're doing is you're going to have exactly the same subset of patients in each of the folds, but the way that it converges to a final algorithm may not be exactly the same every single time. Because, for instance, like with neural networks, you'll initialize it with some random weights, and then it's an iterative process that will optimize those weights to converge towards some final model. So this is actually kind of the point of having the random state to be the same, is that you can see how much the algorithm fluctuates while you hold the subset of patients the same. So this is nice here because you can look at all your different algorithms and determine with this box and whisker plot exactly how well each of them are working. Bring everybody on a screen over here just for now. So this is nice. If you have accuracy plus or minus some amount like this, then you can use that to say this algorithm works better than this algorithm. But again, if you try and submit these results, you're going to have some reviewer that says, how do I know that these are statistically significantly different from each other? And you're going to say, I don't know. And he's going to not let you publish your paper because you haven't done any kind of confidence tests. So what I've done to add on to this is to use these DeLong statistics again to compare the AUC ROC values between the different algorithms. So just to keep things simple, I just took 4 different classifiers here. The data set is the same. And what I do is we loop through all of these different classifiers and we fit the data with each model. And then we log the results for each of the patients by doing model.predict on X, which is our input. We calculate an ROC value using this calculate ROC or AUC confidence interval function. And then we append all of these results for comparison later. And then it will also plot the ROC value. So I will come here and run this function. So here you see a direct comparison of all the different algorithms. So on the diagonal again, you have a no skill. So this is a coin flip. And then you have the logistic regression, k nearest neighbors, Gaussian NB, and support vector machine. And what you end up with here is the ROC values and the confidence interval for each of those as defined by the DeLong statistics. And then what I do down here is use the DeLong ROC test. So what this takes in is the true answers. So this is the Y matrix that we have from the original data set. Our results from one performance model, the results from the second performance model, and it will compare the ROC curves together and tell you if they're statistically similar or different. So if you think back to your statistics classes and you think about accepting or rejecting the null hypothesis, you might be getting some flashbacks to Vietnam here. So basically what this comes down to is you need to calculate some sort of statistics using a contingency table. Some people use a chi-squared statistic. That's really popular. But what you can do is calculate a p-value, which runs on a 95% confidence interval, which will tell you if 2 data sets are similar or different from each other with statistical confidence. So the way that this works is I created this table over here, and maybe I can open it in a data frame. This one here. Right. So on the diagonal, essentially we're comparing an algorithm to itself. Usually you get a p-value of 1 exactly, but NaN is also fine because it's not really giving you much information. When you calculate these p-values at 95%, what you normally have to do is go flip to the back of a statistics book and look at this massive table that shows your p-value for significance based on your confidence interval. So you got to go over to 95% and then scroll down until you find one number in particular. But for us, basically with 95%, if you have a value greater than 0.05, that means that the results are statistically similar to each other. If a p-value is less than 0.05, then the results are statistically different from each other. So for instance, let's look at this logistic regression over here. So if we compare it to k nearest neighbors, the ROC value, or the p-value that's calculated here is 0.004. This is less than 0.05. So we can say with confidence that the results are statistically significantly different from each other. If we go over here to 0.605 with the naive, what is this? The Gaussian NB algorithm, we have 0.6. So we know that the results here between LR and NB are statistically similar to each other. So we can't really claim that like one is definitely better than the other. And same with the support vector machine. So typically the way that you go about this is you want to choose the algorithm that has the highest AUC value. So in this case, k nearest neighbors seems to work the best. So if we go to KNN, we see that it works much better, or sorry, yeah, KNN, oops, sorry about that. I'm gonna rerun this. I don't know how to reorganize it so it's on the diagonal. There we go, we're back. So if we determine KNN to be the highest, so 0.768, then these are the algorithms that we're comparing it to. So we know that KNN versus logistic regression, it is statistically significantly different than KNN because the value is less than 0.05. Also the case with the Gaussian NB and the support vector machine. So in this case, we can claim that the KNN is significantly better than all of the other algorithms that we use. And this is something that you can't do based on only comparing, say, plots like this, where you have like the accuracies. Does anybody have any questions about p-values?
So Luke, in hindsight, can you look at this box and whisker plot and say you like KNN?
It doesn't look like KNN works well here. So the difference between the algorithm that runs in my code over here versus this is this goes through tenfold cross-validation, whereas here I've only just selected all of X and Y. So you could definitely go through and do the whole KFold cross-validation and produce a bunch of ROC curves and be really rigorous with this, but this was just meant to be an illustrative example just to compare one run through each of these classifiers. So any more questions?
Luke, can you go through this image that we have here and explain it a little bit more?
Sure. So this is the AUC ROC curve. I mixed up the order over here, but these are receiver operating characteristic curves. And essentially what this is a trade-off between a true positive rate and a false positive rate based on where you set your decision threshold. So when you make a prediction using one of these algorithms, you'll get a value somewhere between 0 and 1, and you need to place a decision threshold somewhere where you can say, in a lot of cases, if you place it at 0.5, you just round the output and you'll get a 0 if you're less than 0.5 and a 1 if you're greater than or equal to 0.5. What you do is you just use each patient's score as an example decision threshold and calculate a true and false positive rate if you were to use that score as a decision threshold. And you end up with a plot here where each data point corresponds to a single patient score. With these algorithms, most of the scores are very close to, if not absolutely equal to 0 or 1. So you're going to see most of the patients just kind of hidden under here. And then you get like just maybe 1 or a couple here. So depending on the data set that you use, you'll see dramatically different ROC curves. So for instance, let's say in this data set over here, so these are ROC curves for the Brugada project. So here we have 2 different machine learning algorithms. They're both neural networks. The first data set is when we're making a prediction on the disease state before we give them the medication. And then the blue model over here is after we give them the medication. So when you give them the medication, it really brings out the characteristic disease morphology in the ECG. So it's much easier to pick that out. And what we see is an ROC curve that ends up moving closer to the top left. But in a lot of the cases, people have hidden signs of Brugada syndrome, and it only becomes visible when you give them the drug. So what you see is a 0.85 AUC value for before the drug is given and a 0.989 AUC value after, when it's much more visible in the ECG. And if you were to zoom in really close here, each of these little jagged points here is a different patient. So the output of this neural network has a much broader distribution of values than the ones that are in this example data set. So we see a lot more that are kind of in that middle range. And to give a little bit more context to that, I can dive into something called one thing that's interesting to know is that you can automatically select what your decision threshold is. So that's what's highlighted in red here, is if I use this patient here that defines this sensitivity and specificity over here, which is in quotes, the furthest upper left patient that you can find that patient mathematically using something called Uden's J statistic. And I can make that code available to anybody if you want it. But the interesting thing is these confusion histograms. So this is something that we kind of came up with in our group. And essentially what this does is it bins the number of patients that are given through the classifier a score between, in this case, 0 and 0.1. And then on the far right side, 0.9 and 1.0. So you see that in these cases over here, the majority of patients are given a value between 0 and 0.2, which means they have a low probability of diagnosis. And a bunch of other patients are given a score between 0.8 and 1.0, which means they have a high probability of diagnosis. The difference in colors over here, the ones in orange are ones that are correctly predicted, and the ones that are in blue are incorrectly predicted. So if my decision threshold is right here in the middle, that means that the orange patients are true positives and the blue patients are false positives. So they're ones that have been given a DNN output score between 0.5 and 1. With my decision threshold at 0.5, I've assigned all of these patients to have a positive diagnosis, but the ones that are in blue are actually truly negative patients. So these are the ones that are in blue here, and the true positives are the ones in orange. Conversely, on the left side here, the ones that are in orange are true negatives, and the ones that are in blue are false negatives. So this kind of plot here is a really nice way of showing the distribution of scores of your classification algorithm. In particular, we have these are true negatives over here and the distribution of scores. So we see that the true negatives are in majority given confidently negative probability of diagnosis. Although on the right side of the prediction over here, we see that there are ones that are given a higher than 0.5 score. And conversely, for the red ones over here, the true positives, we see that some of them are also given a negative score.
Perfect. Thank you.
Okay. Any more questions about ROC curves? Okay. I think maybe what we'll do is, does this go through all the different ones as well? Yeah, so in chapter 12 here, essentially there's a bunch of different algorithms that you can use for regression as well. We can do linear regression here, for instance. That one didn't seem to work. I got not a number. That was interesting. That is a result, but a bad result, usually numerical underflow. Is there any plots in here? There's not really any plots or anything. So this is using the negative mean squared error as a scoring metric for optimizing this algorithm. And if you have a regression problem, you could loop through these much in the same way that you would with the classification algorithms. So you just kind of take this shotgun approach and load in every single kind of regression model that you have and see which one spits out the best results for the data that you have as well. Didn't really go into depth for this, but does anybody have any questions about how this code slightly varies from the way that the classification one works? Okay. Okay, so there's something called a pipeline, and it's a way of creating a systematic way for processing your data. What's nice about this is it allows you to do something like your normalization pre-processing, and then take that data and stick it into some sort of learning algorithm. So this one here does standardization. So first you create this estimators array, and it's going to be just the order of operations of how you want to process the data. Then the first thing that you want to do is standardize this. So this goes back to the previous code in one of the previous chapters, which does the standardization. So I believe that's mean centering and getting the standard deviation to equal 1. And then it will take that data that's standardized and put it into a linear discriminant analysis. You define this pipeline here as your model, and you feed that in exactly the same way that we've done before. And it does everything for you in a couple lines of code, which is really nice. One of the nice things that you can do in this feature union model pipeline, which I think that is going to be of most use to everybody, is you can do PCA first, which is great. So you do this feature extraction. So that's what this features array is for. So the first order of operation, you want to define that you want to do PCA with the number of components equal to 3. And then you want to select the k best components here. And then you define this feature union over here as your first workflow processing. So this allows you to do PCA as your first step, your dimensionality reduction. And then you insert that into your estimators over here. So first you do your PCA and it gives you a reduced size data set. You feed that into a logistic regression model, define your pipeline, and then you put that in here. So if I run this, the PCA gives a little bit better results, just a little bit. And that's really nice for standardizing your workflow. It's a really clean way to do that. I prefer to do these things manually. I really like to do everything manually, so I know exactly how everything works. So for instance, what I would do is I would first load all of my data from an SQL database, like, well, or an Excel file in this case. Then I can use something like discrete wavelet transform and then go into a DWT basis. That's what I want to do. I could do PCA at this step. And then over here is where I manually do my leave one out cross validation and then process the results at the end and save everything as well. So you can do these things really nicely in one line, but I choose to manually implement it so I know exactly what's going on. And if something's going wrong, I can diagnose it a lot easier. And I'll make both this set of code here where I go through everything and also this with all the statistics for talking about performance metrics for all the classification algorithms available to everybody after this lesson. Does anybody have any questions about these pipelines? I think that we're going to leave it here for this lesson. Okay, thanks everybody.